Okay. Hello. Hi. Am I audible on Zoom? Hello.
Yes, Ashutosh, you are available. Yeah.
Okay. Yeah. Yeah. So my audio is available even in this view, slide view. Okay. Anybody on Zoom? Can you confirm? Is my audio or like is my audio reaching you? Okay. Okay.
So, Jay, is my screen visible?
Yes, Sonal, I can see your screen.
Yeah. Okay. So, good afternoon, teachers. We will start the session in next 2 minutes. So, before that, these are the materials that the students require for this session: plastic straw, scissor, cutter, long thick string, glue, sellotape. If the students have, then it's fine. If they are not having the materials, they can get it in another 2 minutes, and then we will start the session. We are waiting some more participants to join. So. So this is our web page where you will get all the information related to the Sparkle series. So the joining links, Zoom and YouTube materials required, and we'll be posting the assignment and the readings for the session. And for the teachers, the attendance sheet we have uploaded on this web page itself. And then we have this Hall of Fame. So this is for the students who
right
have
now,
shared their assignments with us.
Yeah, Sonal, so right now, sorry to interrupt you.
Yeah.
Right now, we are able to see your one of this poster which you are sharing. That's all we are able to see right now. Are you also sharing something else while you were mentioning the web page and? So if you have shared the window, then it will only show that particular window. If you go for sharing your screen, then might be the things very well.
I'll share it again once.
Yes. Right now we can see. Right now you can see, Sonal.
I think it's fine now, right? Yeah.
Now we can see.
Yeah. So this is the web page which I was telling about. Where you will get all the information regarding the series here. So as you can see, for the last session, we have assignments and reading for the session. And for this session, we have uploaded the joining link and the materials required. And for the teachers, we have the attendance sheet on this web page itself. So you can get all the information here. I think, Jay, we can start now.
Sure, Sonal.
Yeah.
Sure.
Just give me 2 minutes.
Meanwhile,
So,
looking forward for the people to just unmute themselves if they can. Let me just allow them. हाँ जी, किसी का कुछ सवाल हो? Anybody wanted to ask, share, comment regarding the things we have discussed in the last session? Feel free to go ahead. I can see Surendra ji have sitting in the classroom and तो सुरेंद्र जी आप अपने बच्चों को भी दिखा देंगे क्या? Can we see the students as well in your which school is this? Which JNV is this? हाँ सर, आप अपने आप को अनम्यूट भी कर सकते हैं. You can unmute yourself, sir. You can also unmute themselves. Oh, this is wonderful. From the Jharkhand also, the girls have joined. This is great. This is great. Good to see that. And also looking forward for other people. हाँ जी, सभी लोग हो सके तो अपना कैमरा ऑन कर सकते हैं, so that it doesn't seems like we are talking to the what you say the blank screens. We would love to and some of you have any comments, things they wanted to share. This is the time you should. Otherwise, we have Ashutosh from our end, who is all
So,
right. Great. हाँ जी,
Jay,
sir.
before starting, I'd just like to show something. Yeah, just a second.
Go ahead, Sonal.
So you can see my screen now.
Yes, I can.
So, teachers and students, before proceeding further, I would like to announce the name of the Shining Stars of Sparkle series. So these are the name of the students. As you can see, Anishka Prajapati from JNV Jhansi, Krishna Priya from JNV Nalgonda, Mannat Chauhan from JNV Shimla, Mrunali Bhoshale from JNV Kolhapur, and RC Kavya from JNV Ernakulam. So they have shared their projects with us, and so they are the best participating students. And then we have 3 schools. Those are the best participating schools: JNV Jhansi, JNV Ernakulam, and JNV Kolhapur. So we'd like all of you students to get recognized on our Hall of Fame, and you can also share our projects with us. I'll also show you the project of one student. Jay, you can see that project, no?
No, Sonal, right now we are only seeing that particular image only, the shining star.
Yeah.
We were able to see. Sonal, once you have shared, we were able to see that.
Yeah. So this is one of the project that we have received from Anishka Prajapati, and you can see this. She has made it so beautifully, and then she has shared with us. So we request all these students to share your projects with us. ये आपको बाद में confidence भी देगा कि आपने जो सीखा है session से वो आप घर में practice कर रहे हो और फिर हमसे share कर रहे हो, और आपको कोई doubt भी हो तो we are there to solve your doubts. So congratulations to all these students, and I'm telling you all, do share your projects and have a great learning. So I guess all of you would be having the materials that we said. So we can start the session now. Over to you. And in this session, we will learn about the science of sound. Will Ashutosh sir will teach us, and we'll have various hands-on activities and various projects. So keep learning. So over to you, sir.
Thank you so much. Namaste sabhi ko. Hello and welcome to this new episode. I hope you're not surprised to see a new face. Professor Manish Jain took the previous sessions with you. I am his colleague, I'm his junior colleague Ashutosh, and I work at the Center for Creative Learning. And this is our beautiful campus next to Sabarmati, and this is the IIT Gandhinagar campus, and our lab Center for Creative Learning is housed in this. And here, the work that we do, our goal is to bring back the gleam in the eyes of all children and all teachers and all adults as well. And it's a very ambitious goal, and we feel very happy and passionate pursuing it. These are some of the glimpses of our lab, filled with lots of models, lots of chaos where we work every day. This is an auditorium where we take workshops for the science and maths teachers who visit our campus, and we spend many happy hours making all of these models and trying to understand the science and maths behind them. But more importantly, trying to enjoy ourselves as children once again. And as some photos were shared, here are some photos made by Mrunali Bhonsle from JNV Kolhapur, Anisha from JNV Jhansi, Mannat from JNV Shimla, and we were very happy to receive so many finished projects that you sent to us, which inspires us, because we get to know that you are actually following it up after the session is over as well. And these are two beautiful and wonderful garlands that were made from A4 sheet. One is length 25 meter and the other is length 10 meter. So thank you so much for sending this. You can share all your work with us at this email ID. You can come back to it again. And homework links are on this URL, sparkle-series.web.app. So our session today is about the science of sound. And in fact, what I was thinking was, although it's supposed to be about science, but hopefully while learning something about science of sound, our focus would be more on the fun aspect of it. And let's not get too burdened by the scientific aspect of it, the maths aspect of it. I think the session would be successful if at the end of the session you feel excited to make these 10 types of musical or whistles or musical instruments, and you create a lot of noise. And I hope that's not noise, but that's music to your ears and to your teachers' ears. And you go about creating those toys and trying to explore sound on your own in a very tangible, hands-on way. Your teachers are very capable. They'll tell you the concepts of sound very well. My aim and my role right now is hopefully to provide some hands-on activities which make that experience very concrete. Those concepts come to life when we see them through activities, and when you go back to your classes and read those things in your textbook, maybe you'll remember these things. But more importantly, do make all these toys, even if you don't understand any of the science behind. In fact, I'll admit that we don't understand many of the science behind these toys as well. These toys have inspired and confused and challenged even Nobel laureates and scientists. So it's no shame to admit that we do not understand them fully. Sound is sometimes a complex topic, but more importantly, sound is part of our cultures. There is a very famous interview in Rajya Sabha TV by Uddayan Vajpayee. I think he's a medical professor in Indore or somewhere in Madhya Pradesh. And in that Guftagu interview of Rajya Sabha, he says that there are societies that have existed in human history which have lived without technology, but you will not find a single society that has lived without art and music. So there are societies which did not have very advanced technologies or even basic technologies, very primitive tribal people, but every single tribe, every single civilization has lots of musical instruments, songs, their dances. So we cannot live without music and art. So that should be the primary goal of exploring this topic rather than just the science of it. So to begin the session, I'll start with this very simple thing. So as we sometimes blow the trumpet to start things or blow a shank, so this is our first thing. Let's start the session. I hope you heard that. And I hope you're not abusing me for hurting your ears, but that's a very loud trumpet, and it was made using very simple materials. This is a very old discarded bottle. There is a plastic tube over here, and that's a balloon which you're seeing in blue. Unfortunately, the technology has it in it, but I've stretched a balloon over this. So this is a very simple toy. It's made from very simple materials. We'll come back to it later. And when we talk about sound, we often ask this question: how do we hear sound, or what is sound? So if we quickly go over it, sound is basically vibrations. So something vibrates. It has to vibrate in a particular frequency range, and that vibration then has to reach us over a medium, and then our ear and brain processes it. So sound is basically a vibration. The vibration can be of a solid thing. So it can be a surface, which means a membrane. So like you have a dholak or a drum. So it's a 2D membrane. Although it has thickness, it's 3D, but let's assume it's to be 2D. Or A vibrating thing could be a string. So you have a guitar string or a sitar string or any other stringed instrument, or the vibration can be without a solid object vibrating. The gas or the air itself can vibrate and produce sound. So it's not necessary that the vibration has to be of the solid only. And after that vibration has been done, it propagates through a medium, through something called compressions and rarefaction that we'll see. But we need a medium. So most of the cases, most of the time, the medium is air around us. But if you are in water, then that thing is the medium. And sound also propagates in solid mediums as well. So it can propagate through different mediums, and that is needed for sound to come to us, and then our ears take over. So we have these things. So the outer part is the outer ear, but there is more to our ear inside our head. That's called the inner ear, middle ear, inner ear. And then the auditory nerve connects it to our brain, and then our brain has to process it. So sound is not just vibrations. It is vibrations plus that propagation over a medium, plus our ear receiving it and our ear functioning properly, plus our brain processing it and telling us that we are hearing something. So this entire chain of things is needed to hear sound. And when we say what is a wave, let's see it through this simple model. So here you will see a simple wave propagating ahead. And you can see ripples going down and coming back. Right? And what we have done is we've stretched a long piece of tape and we've stuck several straw pieces at regular intervals on it. And then we've brought back that tape and put the sticky side down. So basically the straws are sandwiched between two layers of tape. And at the end of the tape, at the end of each of those straws, we've put some heavy material. So you can put nuts over the straw, you can put clay or atta to make the ends heavier so that they vibrate properly. And then we send a ripple down this particular straw model of the wave. So I'll show it to you again. And you can observe that on one hand, he gives a little vibration, a disturbance. All the straws stay in their place, but the energy moves forward. And you can see that the straws are going up and down, and the wave is moving perpendicular to them. It's moving forward. And this is what is called a transverse wave. So basically, these dots, if you imagine them to be as straws, the straws are moving up and down, but the energy that the person gave from one end reaches the other end, and that disturbance is called a wave. And whenever the particles of the medium vibrate perpendicularly to the direction of the wave, it is called a transverse wave. It's as simple as that. And can there be other types of waves as well? So yes. And sound is a different type of wave. It is called a longitudinal wave. And why is it called a longitudinal wave? I'll first show it to you through this model. So I hope you can see me. And let me try to see myself as well. Yeah. So we've made this thing. So there are two posts over here on the side, and one is a horizontal bar on the top. And this is a spring. It's often called slinky. And we've suspended a spring using several strings, and this thing can vibrate, right? So if I put it here, I can, I'm seeing a literally inverted thing. So if I push this, the spring starts vibrating. So to show it more clearly, I'll show you the video over here. So in the previous video, you saw that how transverse wave moves. The straws move perpendicular to the direction of the wave. Now, when we use a slinky, you'll see a longitudinal wave. So I sent a disturbance from one end, and you can see that the coils are moving back and forth, and their direction is the same as the direction of the movement of the wave. So the wave is moving from right to left, and the coils are also moving right, left, right, left. So the coils of the spring are in their place, but they vibrate about some position. And what you are seeing, this is called a longitudinal wave. I'll play it again. And you can also notice that in the middle, there is some dark portion which is moving ahead. So the coils over there are compressed a bit. So that's called a compression. And on either side of it, you will have a rarefaction. That is, the coils will be stretched out a bit. So this compression rarefactions makes up a sound wave. And if we see an animation, this is how it is represented. And maybe you'll see it in your textbook, but this representation comes from that previous model. So you can see, so first notice the red dots and the red arrows. So the red arrows are pointing to those red dots. And this is, you can imagine that this is a room or a place filled with air, and all these black dots are particles of air, molecules of air. And on the left, something is vibrating and it is sending energy down the medium. So if you focus on any red dot, you will see that it is not moving full distance across the screen. It is vibrating about its mean position. And at the bottom, you can see that the wave is moving from left to right entire length, but each particle is staying in its place. And the darker bands you can see on the screen are compressions, and in between them we have rarefactions. So this simple thing is called a sound wave. That we have air, or we have liquid, we have even solid. Its particles vibrate about the mean position. The wave propagates ahead, and the particles vibrate in the same direction. It's called a longitudinal wave. The transverse wave that we saw with straw, you would even have played with it with a rope. So if you pull the rope up and down, you see a wave. So that's a transverse wave. So this is a very basic introduction to what waves are, two different types of waves. We have electromagnetic waves. Those are also transverse waves, but they do not require any medium. So we'll maybe discuss it somewhere else. Now, coming to production of sound, let's assume that we have a drum. So we have a photo of a drum, but you can also think that this is a dholak or any drum. So if I beat it, if I slap my hand on it, you might imagine that the membrane or the skin on the drum will move up and down, as you can see in the middle animation. So the red yellow thing is representing that the membrane is coming up, the skin is coming up, and it is producing a compression. And when it goes down, that is blue color. So that is producing a rarefaction. And on the rightmost side, you can see that on the bottom, there is a red line that represents the skin, and it is creating a sound wave. So this is what we might imagine. And this is also true that this happens, that if I beat a drum, if I beat any surface, a table, and hopefully you don't do it, but if you beat even a person, you hear some sound, right? So the surface starts vibrating. But what I'd like to show you is that the surface doesn't only vibrate in this particular manner only, and the air doesn't move only in this simple back and forth motion. So my next slide, I'd like to show you the different modes of vibrations that can happen in a drum. So here you can see 10 images, and you can consider them as 10 different ways or 10 different modes in which a circular membrane can vibrate. So the number one that you saw was a simple back and forth motion, but you also have a situation where the left and right ends are moving alternatively. One is coming up, the other is going down. In number 3, you can see that there are now 4 sections, 2 opposite to each other, diametrically opposite to each other, are coming up, while the other 2 are going down, and then it is reversing. And similarly, you can see mode 4, mode 5, mode 6, it gets more complex, and even until mode 10. So the basic point is that the drum doesn't only vibrate in this way. And oftentimes in textbook, due to limitations, we show things vibrating only in one particular way, back and forth. But that 2D surface can vibrate in so many complex ways. And one very beautiful model that we can see using laser is what you can do is you can place a sound source. You can use a rubber balloon, a simple laser light, and you can see beautiful patterns on the wall. So first I'll show you the video, and then I'll show you the model as well, although it is there in the video also. I'll play it again. So we have a laser. There is a plastic box whose cap we have removed, and we've stretched a balloon over it, and we have stuck a small mirror to it. Now, as the laser I'll just pause the video and show you again. So on the right, you have a laser pointer and it is switched on, and its laser beam is falling on the mirror that is stretched on the balloon skin on this plastic box. And after reflection, you can see that the beam spot is on his hand and it is going on that screen. Hello. And now the person is speaking and you can see how we can see a pattern. Please confirm if the audio is visible. Audio was audible.
Yes, absolutely, Ashutosh. We are able to hear.
Now we'll play a song and let's see what kind of vibrations are visible on the screen. So that was a music. Now what we'll do, we'll play pure tones, pure sine tones, various hertz frequencies we'll play on this. And we'll see the patterns. Now we'll play two frequencies together. Yeah. So this was that model. And we basically have a plastic can. You can even use a PVC pipe. You can, so both ends have to be open. So this end is open where we place those speakers. We've attached it to a wooden block and on this wooden plank. And on this end, there is a rubber that we have stretched and attached using a rubber band, a balloon membrane we've stretched, and there is a mirror over here. And over here, we had kept the laser pointer. So you can even speak from here. And if you speak, you shout, you sing, and on the opposite wall, you can see patterns with laser. So do try this, try different frequencies, try single frequency, and maybe it can be a challenge that who can make a circular, a perfect circle pattern using that laser. Mix two frequencies as well, maybe try mixing even three. And one thing for you to maybe think was, why did we see a continuous pattern? And you also saw the pattern even rotating, giving you like a 3D animation effect. So actually the laser beam point is on a single place, but the membrane is vibrating so rapidly and in different directions that it is moving rapidly. It is tracing a path. And what we are seeing actually is the path. And when the path is always repeated, we see a fixed pattern. But when that membrane changes, we see a moving pattern. So this is a very simple toy, very beautiful toy you can use to visualize the vibration. So you're not seeing the exact vibration of the balloon membrane, but you're seeing it indirectly, how that particular spot, that mirror is vibrating. And as the mirror turns in one direction, the angle of incidence of the laser would change. And so the beam will go in a different directions all the time. So this is one very beautiful model that you should make. And coming back to our discussion of the sound waves, this is a slow motion video of a normal speaker that you're seeing. And here you can see the cone of the speaker is moving back and forth. And this is what we usually show through this animation as we saw above. But actually, the sound wave is not a simple strip of air particles moving ahead. So as you see in this, this animation, you can only see a rectangular section of the air, but actually air is all around me. I'm living in a 3D space. So does that mean that air is only moving forward in this small rectangular zone? No, the air is moving as a 3D spherical wave. But since our limitation is representing it on a 2D paper or a 2D screen, we show only a small portion of it. But if I wanted to show you that as a circular wave, I can show a 2D projection of that spherical wave. So there is a tuning fork in the middle, and you can see how air particles are moving back and forth, and compression. So one wave of compression is going, then a rarefaction, then a compression, and a sound wave is propagating. So even though you are seeing circles, imagine that this is a sphere. You are seeing a cross section of a sphere. And you can also see this where we have, so this is the work done by a great educator in US. He runs a channel, Flipping Physics, and he's made this beautiful animations. And you can see the compressions have been marked with the red color to show you better. Now, one thing that I want you to imagine is what will be this audible sound, what will be the nature of the sound that you'll hear, which is represented by this simple back and forth motion of the particles. So you can see that in the middle of the screen, there is a blue sine wave that you're seeing. And this is the diagram that you'll often see in your textbooks where a sound wave is shown using a sine wave. And sometimes students get confused that we say that sound is a longitudinal wave, but then we represent it using a sine wave, which looks like a transverse wave. So why is that? So this animation clearly shows you that the sine wave is actually not representing the physical motion of the particle. It is representing something else. So as you can see, the peak of the sine wave coincides with a compression, the red line that you can see above. And the sine wave, the middle line in the sine wave, which is the zero position, that represents the mean position of the air particles. So if I take the pressure of the air, if the pressure is ambient, same as atmospheric pressure, it is zero on the middle line. But if the pressure increases, the blue line goes up, the sine wave curve goes up, and at the maximum point, it reaches the peak of the sine wave. So that is the compression. And the opposite of it, the rarefaction part, is the crest, the bottom part of the sine wave. So it is the actual physical movement of the air particles that is represented using a sine wave. You can also think of this as the change in position. So one way to look at a sound wave is through change in pressure, but that change in pressure is because of the movement of particles. So the sine wave can also represent the movement of air particles from their mean position. So this means that a particular particle is moving from its mean position sinusoidally. So you focus on any one particle, and maybe that old animation will be helpful. So if you focus on one particular red dot, so first it is moving to the right. So if you consider that positive direction, then it is returning to mean position, then it is going to left, then it is going back to right. So this is a sinusoidal movement, and its mean position can be considered zero. And that is what we see in this particular sine wave. And so my question was, what does this sound like? This particular motion that we see in all our textbooks, what does this sound like? So I'll show you I'll not show you, but we'll hear that sound. Was it audible?
So initially it starts, we can hear that, but after some time it's वो थोड़ा बहुत filter कर देता था आशुतोष.
The noise is getting filtered. But did you hear a tone? Did you hear that tone? So maybe I'll try to play it again by changing my.
We were able to hear. Ashutosh.
Okay. Okay. Right. So this is the sound.
Yes, we can hear. Ashutosh.
Now it is clear. Yeah. So actually the sound that we see in our textbooks mostly represents this very pure tone. So this leads to the obvious conclusion that if all the sound around us could be represented using only this sinusoidal wave, only this simple back and forth motion, then all the sounds in our world, my voice, everything would be just this sine wave tone, pure tone, to different frequencies, some low, some high, but all they would be is this simple sinusoidal pure tone. But we know that this is not the case, and so that means that there is some more complexity to the real or the most of the sounds that we hear. And so what you can hear is, and I'll try to maybe guide you to that idea. We won't go into the entire depth, but here you can see two waveforms on red on the left. So the top one represents a sine wave, and it represents audio of 300 hertz. So how does that sound like? So this is 300 hertz, and this bottom one is a sine wave of 500 hertz. And how does this sound like? So were you able to hear these 300 hertz and
Yes.
500 hertz?
Yes, Ashita.
Right? Now what will happen if I mix these two sounds? So I'll add 300 with 500. So this is 300. This is 500. And this is 300 plus 500 together. And on the left, you can see that I took a 300 hertz sound wave and I added it to this, and I got this bottom wave. So on the bottom is the resultant of the above two waves. And you can focus only on the blue part, that is the resultant of the two waves. And how do I get the resultant? I just add the amplitude at each particular point. And whatever amplitude I get, I just plot it. So on the top, you can see the individual waves in red, 300 and 500. And this is the final wave that you see on the bottom. And how does this bottom wave sound like? It sounds like this that we just heard. So it's a more complex sound. And now referring to this animation that I showed you, which you can see on the right, this is not the animation for this particular sound wave on the left. This was for that particular simple sine wave that you can see on the bottom. So you can imagine that if for that simple sine wave, the motion of the air particles was just like this, then for this complex blue sine wave, so then for this blue sine wave, how will the particle be moving? So first it is moving to the right, let's say to the right, then it is coming to a mean position, then it is going left a small bit, not as much as it went to the right, then it is coming back to the mean position, but then it is going again back to the left, then it is coming to mean position, then it is going to right. So the motion of the particle is a bit complex. It is going like this, then coming back, then coming back, then going like this, then again moving like this. So as we keep on adding more and more frequencies, we get more complex waveforms. And that is what is called, so the bottom graph that you saw is, this is called a waveform. We can also represent it in a different way. So on the x-axis are the frequencies, and on the y-axis is the loudness in decibel. And as we know that our sound consisted of only two frequencies, you can see these two peaks. So the first peak on the left is the 300 hertz peak, and the second peak is the 500 hertz peak. So there are two ways of representing a sound. Either you can make a sinusoidal curve, which we call a waveform, or you can make a frequency spectrum where we plot out all the frequencies and their relative amplitudes. The height of these peaks shows the amplitude, the loudness. So right now both our sounds are of the same loudness, so the height is the same. But often this is not the case. In fact, I'll show you examples of 2-3 more frequencies. So this is the waveform when I add 300 hertz to 2000 hertz. And on the right, you can see that there are two peaks. One is 300 hertz and one is 500 hertz. So this sounds like this. If I add 900 hertz and 1100 hertz, this is the waveform that I get, and I again get these two peaks. So you can see that this is a bit different, although it's not very different from a pure sine wave, but some level of difference, complexity is now arising. So now let's take another interesting example. My colleague Jay, who's with me here, he said namaste, and his wife Shilpa also said namaste. And though they are both different individuals, right? So he's a male, she's a female, but both are saying the same words. But we know that they both sound different. It's obvious that they sound different. But why do they sound different? It is because both their voices consists of different frequencies, and the amplitude of those different frequencies in that frequency spectrum is also different. So I'll take you to that slide again. Yeah. So this is for a human speech. So on the left is Jay.
Namaste.
So when he says namaste, this is the waveform that is generated. And you can see that there are so many different frequencies in his namaste. Some have more amplitude, some have lower amplitude, but it is not just one frequency. It's a mix of so many frequencies. And this is the auditory fingerprint of Jay when he says namaste. So like we have a DNA fingerprint, but for each individual, there is a different voice. And even for saying any particular word, there is a different frequency spectrum that is there. And when Shilpa says namaste, so let's hear that.
Namaste.
So Shilpa's waveform is like this, and you can compare these two waveforms. They look different. You can also compare their frequency spectrum. Different frequencies, some look similar on the higher end, but different amplitudes as well. And this is what we often also call timbre. So there is a term that is used in textbooks. It's called timbre of an instrument, which means that if I play 400 hertz on a flute and then I play 400 hertz on a violin, both are playing 400 hertz, but they both sound different. Even by closing my eyes, I can tell that this is from a flute, this is from a violin. Why is that difference? Because when I play 400 hertz on the flute, it produces other frequencies also besides 400 hertz. And the collection of those frequencies and their relative amplitudes, it gives a particular nature to that sound. So that makes it unique to that flute. Similarly for violin. So every other instrument, every human being, they have this different collection of frequencies that is generated each time. Right? And so I'll also show you a waveform for a flute. So this is an F4 note that is played on a flute. So you can see on the top that this is how the waveform looks, and you can see that there are so many frequencies that are in its frequency spectrum, and this frequency is much more stronger than the remaining frequencies. And then you'll probably study in your classrooms that we have these things called harmonics and overtones. So if the basic base frequency that an instrument is generating is 400 hertz, the next harmonic would be 2 times 800 hertz, then 1200 hertz, 1600 hertz. So 1 time, 2 times, 3 times, 4 times. So these are all called harmonics or overtones, and the collection makes that particular sound of that particular instrument, right? So this was some very basic thing about the nature of sound waves. But as I said in the beginning, our focus should be to also enjoy sound, to also experience making these instruments and whistles, because even thousands of years ago, when no science, no physics, nothing, no scientists existed, no schools, no textbooks existed, ancient caveman also made musical instruments. I think they've discovered flutes as old as 30 or 40,000 years ago. They have no understanding about the complexities of music or how the physics works, but that did not stop them from enjoying music, and that should not stop us also from enjoying music. So people have made different instruments, different musical whistles using simple things that they discovered about the nature of sound. So there are so many ways to make the air vibrate, and there are so many variety of musical instruments that we see. So we'll start making some of those instruments. Okay. So where do we start? We'll start with a very simple straw that Professor Manish Jain would have shown you. So I'll need a scissor. Yeah. So all of you have these straws. What you can do is you can chop off one end of it, and then what I have to do is I have to squeeze one end in my mouth and press it several times so that this part becomes flat. right? So I'll probably show it to you on the overhead. So you can see that this thing has become a bit flat now. Where's the focus? I hope you can see a bit.
We can, Ashutosh, we can see.
Yeah. So you make this thing flat, and then you make a cut like this, one triangular cut here, and another triangular cut you make here. So you'll get like something like this, and these are two flaps that you can see here. Now, when I put this thing in my mouth and blow, so this is a beautiful sound that I get. So you make your own flute, or I wouldn't exactly call this a flute, but you make this straw, very simple, very beautiful thing. And if your whistle is not sounding, then there could be two reasons. Either your these two things, I'll again go on the overhead. So one reason could be that your these two reeds or flaps are too far apart, so you have to flatten it a bit more. Or it could be the case that they are too close together, so that when you're blowing, it is closing, the straw is not opening. So you have to adjust with the distance between these two things. And when the distance is right, you'll find that they are vibrating like this. So they vibrate in this manner. And what we get is, now what will happen if I cut this straw? So let's see. So as I chopped off the straw, you could see that there was a change in the sound as well. And that change is basically what in technical term we call frequency was increasing. Pitch is increasing as the length is decreasing. So there is an inverse relationship between the frequency or the pitch we hear and the length of this air column. And you can do very interesting things with this small pipudi that you make, or the small whistle that you make with a straw. So this is like a small baby crying. And the interesting thing besides the fun in it is, well, you notice that so if I blow it like this, it's a simple sound. But if I put my hands around it and I change the shape of the cavity of my hands, the sound that you're hearing is changing. So that means that the shape of the air column, or you can say that if vibration is being produced in my throat, the shape of my throat and my mouth, including my nasal cavity, and how I change the shape with my tongue, with my lips, all of them come together to produce the different sounds that we hear. So again, we produce a simple vibration, but by changing the shape of the vocal tract, as we can say, the vocal tract, the mouth cavity, we can make different types of sounds, different resonances can happen. And this is a very interesting area of research that often people do, that how do humans produce sound. In fact, it is very interesting that how are we able to produce a whistle. How many of you know how to whistle? Sometimes it was very difficult for me to figure out, because I would do like this and no sound would come out. And what you have to do, and what maybe you can try, or those who know how to whistle, you can pause and reflect that when I whistle, I have to pull my tongue back and it touches the upper part of my mouth. So if my tongue is flat and I blow, no sound comes. But as I pull my tongue up and it kind of touches my upper mouth, so I can hear that sound. So by changing the shape of my mouth, I'm able to produce sound. And in fact, there is another very interesting type of whistle that I heard, that I learned to make some time ago, is you take your hands and you put them like this, and then you have to close them and make an opening. So your hand should be airtight and there should be only this one opening here. Okay, small opening over here. And then when I bring this opening to my mouth and I have to blow on it, So even your own hands, you don't need any instruments or material. You can make a whistle through your own hands. And it will be interesting that the sound produced by the hands of an adult would probably be different from that produced by a child, because our hands will make different size cavities, right? And as I was talking about sound production, so you take this reed that you had and you take a balloon and you put it inside. So what I have done is I've taken this thing and I've put that reed, that straw whistle that I made inside, and I've taped this balloon. Now you have to adjust that reed as I told you, but then I attach two straws to this thing. Now let's hope this works. Let's see what happens when I blow. Yeah, so it didn't work this time. Let me try it again. Now imagine that this is my throat, my lungs, and the balloon represents my lungs, and it is pushing air out, and the throat is the vocal cords in my throat are vibrating. And then you can imagine that this is my vocal tract, and I'll also add my mouth to it, because I can't add a very flexible mouth. Our mouth, lips, tongues are so amazingly flexible that they help us sort of create, sculpt sound. So let's see. This isn't good. I'll try a bit. What I'll do is I'll put this end of the straw in my mouth, and I'll not produce a sound with my throat. I'll use the sound produced by this, and I'll just move my lips, and let's see if we can generate some sound. So I think a bit was heard. So this requires some fine tuning, but I think it will be very interesting. You can call this a voice box. My friend Slater Harrison, who runs a website called sciencetoymaker.org, he showed me this toy, and it's a very beautiful toy. You can add more straws. And there was a time in US when the singers had this synthesizer, and they would put the thing in their mouth, and instead of speaking with their natural voice, they would use the sound produced by this particular thing. So coming back to our bugle that we made in the beginning, right? So how was that particular thing made? As I showed you that there were, so what you do is take a balloon. I'll show it to you on the overhead. So you can see that there is this balloon, and you make a mark like this on it, right? And then what you do is you just cut this particular thing. So now you will have this hole over here, and then you have to take a bottle, you cut out its bottom end, and the hole that we had made, we stretch it on top of this particular thing, right? So maybe over it is better. So this particular hole that I had made, I'll put it on top of this, and I'll tie it with a rubber band. And then you take a small piece of, you can take a plastic tube, plastic pipe, PVC pipe. You can even take the empty cardboard things, jo silai ke dhage, sewing thread. You have the cardboard tube inside. You can put it over here. And then what you have to do is, if you just blow it like this, it will not work. So if you blow it like this, so it doesn't work if I blow it simply. So if you blow it like this, it doesn't work. What you have to do is, you have to pull this thing so that the rubber membrane gets stretched over the mouth of the bottle. And then when you blow over it, when you blow from this side, what will happen? The air will try to push this membrane up, but the elasticity of the membrane will push it down. But then you're blowing air, it will push it again up. but the elasticity will pull it back down. So this membrane on top will vibrate very rapidly back and forth, and that back and forth thing, it is almost acting like a valve. It is opening and closing quickly, and that valve will then push the air inside over here, and the air will then start vibrating over here, and a standing wave and resonance happens. You learn about resonance and standing waves in your class, and that resonance causes this very loud sound. So you can make this trumpet. So I also have another version of it. So you can also use a PVC. So if you want, you can make this out of PVC as well. So what I have is simply, this is a T section that we get, and at the one particular end, what I've done is I've taken a polythene, and I've stretched it just like I stretched my rubber over it, and I've taped it. And here I have a PVC pipe. It has a connector over here, so that connector will seal this end. So this particular connector will seal this end as I put it inside. And now I have to push this pipe so that it touches this thing. You can see the pipe from here, and I have to push it a bit. Don't push it too much, it will break the thing. So you can see that on the overhead, I push this pipe so that now it is touching over here. Now when I blow from here, the air will rush in, it will push this membrane out, and then it will go in through this thing. And the same thing will happen. So this is a very interesting and very loud bugle that you can make. So I hope that in your school you do make this balloon bugle, PVC bugle, and you create a lot of noise. This could also be your cheering thing in your matches or any of your ceremonies that you do, right? As I shared with you that that particular membrane was acting like a valve. Now we need that valve because we can't just blow air through something and expect sound to be created. Sound is created when the air vibrates in a particular way, and something called resonance is created. It creates standing waves, and for that the sound has to be pushed in a controlled manner. So now imagine आप झूला झूलते होंगे, you play on a swing. So your friend is swinging on a swing, and you're standing here, and your job is to push the person. So now when will you push the person so that his amplitude increases? You'll push in sync, in synchronization with the frequency of that oscillation of that person. So when the pendulum goes like this, when it comes back, as it is starting to go back, you'll push it. Then it comes back, then you'll push it. Right? So your push will have to match the frequency of this. So in our case, with our balloon, the air inside has a particular frequency of oscillating, and this balloon membrane matches the frequency of that oscillation, and therefore resonance occurs and we hear this loud sound. So this is one type of valve that we have. What was the valve with this straw whistle? The valves were these two flaps that we had. So these two things act as the valve. How? They press and open, they press and open like this, and that's how they control the flow of air. Now you must have also played shank, conch shell, it's called shank, aap bajate hain, or sometimes you have those bugle, the trumpets, that sound. In that, the valve is acted by our lips. So those of you who play the shank, you will know that you can't just blow air and make the shank sing, right? You can't just do, it doesn't make a sound. What do you have to do? Your lips have to buzz. So you have to do something like, right? You do something like this. Why do you do that? It looks funny, but you have to do this because your lips vibrate very quickly, and air comes out, then it is stopped, then it comes out, then it is stopped. So if you look at a shank, this is a cross section of a shank. So on the left, you can see that they've cut it vertically, and you can see that it is actually a spiral that goes down. You can see the spiral, and on the right is the top U. So in image D, you can see that it is a spiral that is going, and in A, it is a side view. So it is actually a long pipe which increases in diameter. So it will also have a resonant frequency, and when you buzz your lips, it matches the resonant frequency of the shank, and therefore you get a very loud sound. In fact, you can play a shank and record its frequency spectrum as well. So you will see that it also has so many different frequencies, not just a single frequency, but there are many frequencies. This bass, the lowest frequency, has the highest amplitude in our particular case. And there are, if you go online, if you use an Android phone, you can go on Play Store. So if you find frequency spectrum analyzer, so there are apps that are used. And the previous graphs that I was showing you, which had those blue purple graphs, that was done using an Audacity software, Audacity. So you can record an audio, and when you enter it into that software, it gives you that waveform. And in the menu, you can go and generate a frequency spectrum. So it will show you the different frequencies that are present over there. Now, one of the main mechanisms, so as we were talking about the valves that were happening, so one is the reed valve that you saw. A variety of it in 2D was the balloon membrane or the polythene membrane that we saw. Now, in our childhood, we used to play this irritating game where we would take a polythene strip, or we would even take a paper, and we would blow across it and sound would be produced. Some people also do it with leaves. So if I blow across it, so I have to place it close to my mouth, I have to bring my lips together, and I have to blow so that a jet comes out. It won't work if I blow it far away or if I blow very softly. So I have to bring my lips together. So it's a bit irritating. And the reason why I'm showing you this is one of the most fundamental mechanisms of generating sound in many of the musical instruments and air instruments that we are seeing, and it is called an edge tone. So here on the right side, you can see a sharp edge, this triangular thing. And on the left, there is air coming out from a narrow channel like a jet. So when that air comes out, it hits against this sharp edge and it breaks into this circulating air streams. So some air goes above, some air goes down, and this is how it looks. So from the left, there is a small opening from where a jet of air is coming, and you can see the sharp edge where the air is hitting, and it is breaking into these two streams called vortices. Singular is called a vortex, plural is called vortices. And when this bottom vortex goes inside, so on the bottom you can see an opening. So when it goes in the bottom side, if there is air over there, it will start vibrating it. So now this is acting like a valve. So the air itself acts like a valve. So this is called an air valve. So the principle is basically this same thing. So this was the sharp edge, and I was blowing across it. In Uttarakhand, where I come from, you often hear very beautiful and gentle sound in pine trees. चीड़ के पेड़ के जो जंगल होते हैं, like pine trees, forest, you will hear that sound of wind. And how is that sound produced? It is actually produced when the air hits the pine needle leaves and it breaks into these vortices. And those vortices create pressure changes in the air, and that is the source of sound. It is not because of the vibration of the needles themselves, but the air which is vibrating and creating pressure fluctuations. Similarly, there is a very interesting whistle. Right, so I have my friend here who's helping me, Dinesh. So you must have seen your referee. So all of you must be playing sports, I believe. And referee के पास एक सीटी होती है, so it's called a referee whistle. So why does that work? I'll first show you the image. So this is an image of a referee's whistle. And here also you can see that there is a narrow channel on the left from where you blow, and there is a sharp edge on top over here, right? And the air hits it, and an edge tone is created over here. And some of the air goes inside and it circulates and comes back again and interacts with the above air. Sometimes they put a ball over here so that the air pushes the ball up it stops the air from blowing and then it falls down. So it creates a fluctuation in air. So you can also create that same referee whistle using very simple instruments. So what you have to do is take a aluminum can, a soda can that we have, and I'll show you. So this is a strip. We get those cold drink cans, aluminum cans. So you can cut a small strip from it and you take a straw. And what you do is you flatten the straw and you push the aluminum strip inside. Now the width of this thing has to be equal to this, the width of the straw when it is flat. Maybe it is working from this side. Right? So it will go inside like this. And after that, you have to curve this remaining portion. So जो strip का जो बाकी का हिस्सा बाहर बचा था, you have to curve it. And when you push that strip inside, it is here, this part will become flat and it will create that jet. So now let me play it. What I have to do is, so these two ends are open. So I'll put my fingers like this to create that cavity. And I have to adjust this top thing so that it faces the coming air. So you have to adjust this top part and close it from the sides. So let's see. So you can make a referee whistle using these waste materials, and it sounds pleasing if you yourself make it. If somebody else makes it and irritates you, it sounds very irritating, right? So this is another very interesting toy that we have. And one thing that you must have done with a bottle. Just a second. So you all must have, I'm sure all of you have done it. And if you haven't done it, please do it. So you must have heard a sound when you blow across a bottle, right? Now this is very interesting. Why does this make a sound? And the sound doesn't come if you blow straight. Some sound comes, but it's not the sound we're looking for. You have to blow it at an angle, right? So I'm almost blowing at a very shallow angle. And it's making the sound. And if we pour water inside it, the sound changes, right? So you must have seen that if your bottle is full, if you start drinking and you keep blowing, the sound will change. But if this is an empty bottle, I pour water in it. So now I've filled some water. Now let's see. Some sound has changed. Now I've filled it all a bit below half. So you can see that here also, like the straw, as the length of the air column is decreasing, as the water is getting filled, the frequency of the sound is also changing. It is increasing. There's an inverse relationship that we told you about. Now you can make a very interesting whistle using CDs, and I'll show you. So what you have to do is, this is one of my favorite whistles. What you do is you take 3 CDs. So these are 3 old CDs, DVDs, anything you can take. Take 1 CD and you cut a slot in it like this, right? So you cut a slightly inclined slot on this. Then what you have to do is take 1 CD, place this CD with a slot over it, but don't align the center holes exactly, right? So this hole should be slightly away. You can see that this circumference is not matching. So it has to be a bit outside, not exact. So it doesn't have to be exactly on top, slightly outside. And then you place a 3rd CD in line with the bottommost CD. So the 1st and 3rd top and bottom CDs have their holes aligned, and the middle CD is slightly outwards. So then you will get an opening over here. So that will be the place where you will blow and it will create a jet. And you can see that the center part of the middle CD which is coming out, that will act like that sharp edge that we saw in the edge tone photo, right? So it will act like this edge, this center, this triangular edge that you were seeing, it will act like this edge. So how does this work? If I blow on it, you won't hear a sound. So I made a different version. I've already glued it together. So you have to glue all those 3 CDs together. So I've glued this thing. If I blow, the sound doesn't come. But if I make a cylinder out of my hand like this, right, and I place it on top, I'll show it on over it. So I have to make a cylinder sort of with my hand, and then I have to place the CD hole on top of it. And now I'll blow and let's see what happens. So this thing is creating that vortices that we saw in that previous slide, but it needs an air column to make the sound, to resonate, to amplify the sound. So you can use any sound chamber now. So what will happen if I use a bottle? So let's use this as a cavity. Now with bottles, I noticed an interesting thing, that it doesn't work properly if you place the CD exactly on top. You have to incline it slightly. Maybe it will be visible from the slide. So you have to, or maybe from the overhead. So it doesn't work if you place it exactly flat. You have to tilt it slightly, and then it seems to be working properly. So if I blow it simply, and if I place this thing, I hope you can hear the sound. So this makes interesting sounds, and you can use various things. So you would notice that the sound that I make, the frequency that is coming like this, just with water, it is same as the frequency like this. Only the amplitude is different. One is a bit loud, one is a bit soft, but I like this the best. You can use your own hand. So this is a very nice CD whistle that you have. You can use your coffee cup, your milk cup, use all sorts of pipes below it, and you'll hear different sounds. In fact, let me take my PVC bugle and see if the sound is getting produced. So it does make some sound, right? So this is your CD whistle, a very beautiful whistle that was made by I believe the tribals in South America, probably the Incas. They made many whistles using water, and they would make the whistles with clay, and they would fire and bake the clay, but they would make very beautiful whistles. Unfortunately, we don't have a clay version, but we do have this toy with us. The yellow color is getting a bit hazy. I'll show it to you on overhead first. So this is how it looks. It looks like a bird, and at the back there is a pipe. There is a small section over here which creates the whistle, and there is an opening. And what I have done is I have put water inside it. So what happens when I blow it? It makes this very beautiful bird call sound. So this is a very beautiful whistle that was made by those people, and I have also cut a whistle into 2 halves. So this is how it looks, and if you cut it into 2 halves, this is how it looks on the inside. So there is a cavity, the water is filled here up till this level, and you blow the air from here, it hits this notch and it makes a whistle. But as we are blowing air, it pushes the water and it changes the shape of the cavity inside, and so you hear that fluctuating sound. There is also a very beautiful flute that we made. I believe I'm saying this for almost every flute because I love all of them so much. And you can use a bottle, a plastic bottle, and you can use a straw. I think it's better on overhead. So you have to use a plastic bottle, you have to use a straw and some tape and some scissors. So what you can see is, you can see a mark over here. So I've made a sort of square cut over here. So I've removed the plastic from this place. I've made one slit over here, you can see, and I've made another slit over here, right? And what I've done is, I've taken a straw and I've pressed its forward part a bit so that when I blow the air, it comes out as a jet. And you have to adjust it so that when you blow, sound is created over here. So I blow from here. Let me show you like this. I'll blow from here. The air will form into a jet at this point because I've pressed it. So you press it and you put tape over it when you're final with your position. And then as that thing hits over here, it hits this edge and it creates that edge tone. And this creates a very beautiful sound. And if I open the cap, the frequency changes. So this is with the cap closed. And the particular bottle, we haven't yet made this very rigorous in terms of the design, but the place where we saw it, there's a guy in UK called David Vernon Williams, and he makes fantastic toys. What he suggested was, you try to use a bottle whose diameter is half the length of that bottle. So in our case, it is slightly more than 2 times the length. It is slightly less than 2 times the length, or I would say that the length is slightly more than 2 times the diameter. But you can try different variations. So if this diameter increases, the length should be approximately 2 times. You can also use a smaller bottle. Now what happens if I open those slits? So you saw that I had made 2 slits on the side. So what will happen is, if I slide my fingers, more and more of the slit will become open and the sound will change. So let me show it here itself. But there'll be a problem with the microphone. Okay, I'll show it here. So this is actually a flute, I would say. The straw thing that we make, those are very fun things, but they are more bassuri rather than basuri. This is something that I feel is more like a flute. And I am very disadvantaged in music. I don't know how to play a musical instrument. I wish I could have played, but I tried to play one very simple jingle. It's Jingle Bells. And why I chose Jingle Bells is because it has only 5 notes. So I can play that thing using 5 notes, and I'll show you how that jingle bell music scale looks. So on the screen you can see that on top there are piano keys, and in Western music they mark it as C, D, E, F, G. We call it Sa Re Ga Ma Pa. They have C, D, E, F, G, A, or they also have Sa Re Ga Ma. They also have Do, Re, Mi, Fa, Sol, La. So C is basically the lowest note. D is higher than C, E, F, G. So here you can see that for each word in the song, jingle bells, you have different notes. So I'll try to play from this top line. First 3 lines I'll try to play, or first 2 lines, let's see. So what I have to play is 3 E's, then 3 E's, then 1 E, then G, C, D, E. So how does that look? It looks something like, maybe this angle will give you a view. So C is, when the entire slit is closed, that is C. Then D, E, F, G. So I can play those notes over here. Now let me try playing this. so a bit not exactly musical, but I hope you are able to get the feel of it. So you can, so those of you who like music, who play some musical instrument, make this flute and try to play some other songs with it. What else do I have? There were many interesting things. Yeah, so this one thing that you can also do with the with your bendy straw is, so you had these straws with which you made your flute, but often these straws have this thing that can bend in the middle, right? The bendy part. So don't throw it away. What you do is you cut this part. You cut the only the part which is corrugated, which has those creases, and you stretch it. So basically, you then, after cutting it, you can stretch this part and you cut these two ends. So you'll get something like these two sections. And what I noticed was it doesn't work all the time, but and it also doesn't seem to be working if the thing is perfectly straight. So you'll have to tweak with it, you'll have to work with it, try to bend it. Sometimes it doesn't work from both the sides, it works from only one side. I don't know why that is the case, but this is also sort of a whistle. So it's soft, but you can hear. So it's possible even with this thing. Now there is another very interesting thing that we made, and that's using a PVC pipe. And you can make this simple flute using a PVC pipe. What we've done is we've taken another PVC pipe which has a diameter smaller than this, and we've put some foam sheet on top so that it becomes like a piston and I can slide it inside. And then what I've done is just a second. So the cap seems to have got stuck. Anyway, I'll try to show you like this. So what you've taken is, so that's a straight pipe and we've put a elbow section over here. And over here, we've tried to create that sharp edge. So what you do is you drill a hole, make it square, and then you take a file and you file this thing, you sand away this thing so that it becomes like that triangular edge. And from here you blow, and you also have to put a a foam stopper inside. So we'll probably give you an instruction. This is not coming out, otherwise I'd have shown you. But basically we've taken a cylindrical piece of foam and put it inside, and on top we've created a small slit so that air can pass like a jet. So that jet now comes and hits this particular thing. So if I blow on it, so I'm basically pulling this thing inside and outside. And we have a friend over here, Kirti, who likes playing musical instruments. So he recorded a video, and he's even able to play Vande Mataram or Jan Gan Man through it. Right. So that was very beautiful. So you can make all of these instruments, and people have been making these things for centuries, millennia, and music, as I said, has been part of our culture. There's another interesting thing that you can do with plastic bottles, and it is when you use a cycle or motorcycle valve. So basically, you drill a hole in the cap, and you insert a tire tube valve inside it, and then it will become something like this. This has to be sealed properly. And now when you put pressurized air inside it, the nature of sound changes. And then what we've done is we've taken a simple cycle spoke, we've put some cotton on it, and then we've wrapped it with a thread to make that hammer. So if I now hit it, so now you can see that it's become like a musical instrument. It is now ringing. And what will the frequency depend on? The frequency will depend on how quickly the plastic of the bottle can vibrate. And that will depend on the pressure inside the bottle. So if I put different pressure air inside, the sound will change. So this is a bottle with a different pressure. This has different pressure. And this one has different pressure. So this is called a bottle phone. And sometimes what people do is they take 10, 20 bottles or even 8 bottles and they fill different air pressure. They fill air with different pressure inside. And so you get different notes and they can play a note or a melody using that particular thing. And I believe we are moving to the end of our time, right? Jay?
Yeah, Shutosh, maybe we would like to conclude here. Gopal Krishnan sir is also there, and maybe you would like to take few responses from the audience as well. Maybe you want them to, if a few of them have the straws, they can make some sounds at the end. Yeah, Sonal, you can guide us further.
We had many more things to discuss. This is such a vast and beautiful topic that will probably take another session, but I hope that we discuss some science of it. There are so many instruments that we showed you. If you have straws, please do make them. If you have made them at the end, Sonal, you can coordinate and do all of this, and do send us all of these projects, videos that you make, or the instruments that you make, and we'll be very happy to receive it.
Yeah, very good evening, Jay and Shutosh and everybody
Good evening,
there.
sir.
Yeah. It's it's very, very amazing to see the attendance of the students for this Sparkle series session 3. I have been just observing the children are very keenly listening to the presentation, and I'm sure this particular program is a God-sent program for especially our JNV students and the students who are part of this Vigyan Jyoti in the near vicinity of the JNVs, as you may be aware. It is not just for Navodaya children. We are also covering some of the children from government schools in the near vicinity of the JNVs. I just want to appeal to the teachers who are present here that, in the context of the learning gaps that have happened during the pandemic, when these children were in class 10 and 11, I am sure that is the area we just wanted to address with a prayer to the IIT Gandhinagar, and you people have come forward, and it is being collaborated with IBM and AIF. Dear children, please take it from me that it is an excellent support activity that is coming to your doorstep. Don't miss this. How you would be able to gain more from this is after the session is over, trying your hands on the activity in collaboration with your friends and with the help of the teacher. If you start asking questions, no teacher will say no to you. So it is you who have to take the call. Everything is available in your fingertips. What materials you should be ready with, what is the topic that is going to be dealt with, and how it is going to be dealt with, all that is posted in the web page. So I want you to go through the web page before you attend this program. These 10 to 12 activities which are going to be conducted to you are all part of the foundational concepts. For example, today, Dr. Astosh has taken the topic on sound. Though I am not very well versed with the scientific perspective of it, but I am able to appreciate and the simplicity with which he has explained, everything is being correlated with an activity and an example. So dear children, I want you to take this as an opportunity that is coming to you. God does not give many times. So this is one-time opportunity, right? Whatever gaps you had in your class 9 and 10, with these activities, if you can participate and you can start working on it and start asking questions, start explaining to your friends, right? If you, and don't postpone it much. Today the session is over. In 2 days time, you should be able to have absolute clarity on the concept that is introduced to you. So if you can develop this elementary concept, and I'm sure you will be able to appreciate, you will be able to enjoy, you will be able to apply it, and you will be able to crack any question that is asked on any of these topics. So this is with a very, very focused and very with great commitment, this initiative is being brought to you. And I am sure the physics teachers who are attending today's program will also appreciate this venture. And it is a sort of making your job easy, giving you the extended perspectives about the topic. So I want you to connect the children with the same topic in another day or two, so that it will work as an absolute reinforcement for giving a concrete shape in the minds of the children to visualize the concept. So Ashutosh, we have done a wonderful job. My words will be very inadequate to give thanks to you, because now 200 schools, maybe around 30 to 40 children in each school, they all have been the beneficiaries out of this program.
Thank you so much.
No.
Thank you. I really appreciate you all for organizing this.
I request the teachers to encourage the students to make some posts on this activity. So when the child makes a post on the activity, there is a metacognition. The child also will start thinking about what she has listened to in the session. So it is not just for showcasing, it is just to make the child think further, to reinforce the concept that the child has understood. So it is my sincere appeal to all the teachers to take this program as an opportunity and pass on this benefit to all the students. And we don't mind if you can bring some more children also and make them sit in the program, of course, without disturbing the ecosystem of learning in the classroom. So am I right, Jay? I think the teachers are free to bring some more children.
Absolutely.
Also.
Absolutely, sir. We would be very happy to.
Yeah. So we are all blessed people. We have a dedicated smart room in our school. 1 or 2 rooms are also there. You can just, one group of children can be in one group, in one classroom. The other group can be in another classroom. But I wish that the teachers will understand the value of this program in giving conceptual clarity and bringing granular understanding about some of the basic concepts which are required to understand science and appreciate science and apply science. And we will make this Sparkle series a grand success. Once again, thank you, Ashutosh. Thank you, everybody who is associated with this program. Thank you. Over to Jay.
Sure, sir.
Thank you, sir. Jay, should we hear some feedback from some of the teachers and students now?
Absolutely. And all the things which Ashutosh is demonstrating, we have put it up into the links has been shared, will be shared with you as a part of a document and the web page we are mentioning. So the objective of the session was to demonstrate them and get you excited about making this particular stuff. And of course, in the eventually you can try by doing some hands-on activities, making some of the musical instrument, playing the whistles by yourself. And Ashutosh, we can also request the people who are there with the straws and scissors, if they have brought, we can also request them to make these straws and flute right now, whistles right now, and they can do. Others who wanted to share something, ask something. I can see Anumega has couple of questions in between. There are few other queries. Feel free to unmute yourself or ask the question in chat, or just raise the hand and we can unmute them. Meanwhile, Anurag, Sonal, if you wanted to add something, feel free to just interrupt me. Yeah.
No, Jay, we can. We'll be happy to hear from students and teachers.
Absolutely.
Piyush, you have your hand raised. You can unmute Piyush. You have a question?
Sir, when is 3030 Eklavya season 2?
So just after the Sparkle series, we would have the 3030 Eklavya, Piyush. So we are planning to start on the next academic year. That would be probably in the April. So Ashutosh, one of them has raised couple of questions. I'll just repeat for her. So that was Anumega. Sir, in the case of bottle, Anumega, would you like to unmute yourself and share your doubts here? You can just raise your hand and I can unmute yourself, or anybody else who has a question or wanted to ask something. Maybe at the end right now we can switch on your cameras now, and we can see you. You are not able to unmute yourself. All right, let me just try. Now you should be able to, Anumega.
Yes, sir. Hello, sir. I just wanted to ask a doubt. When you conducted the bottle and the balloon experiment, you said that only when the balloon is stretched, the sound will be produced. Does that imply the mechanism of our ear as well?
So in some sense, yes. Why it has to be, so in the case of a balloon, it has to be stretched primarily to achieve sufficient elasticity, because it has to push down again, it has to act as a valve. So when air pushes it up, there should be a restoring force pushing the membrane down. If it is very loose, the air will push it up and there will be a continuous channel for air to keep moving. It won't act as a valve. So when we stretch it, it actually creates that membrane type thing. So for this particular thing, that is needed. For the ear, I think so. Although it is an interesting question that how stretched is our eardrum. I'm sure it is, because if it is loose, what will happen is the oncoming pressure waves will not be able to transfer their momentum to the eardrum properly. A lot of it would get absorbed. So maybe you can also think it like, so if you have a bed sheet and you stretch it and you throw a ball or a balloon on it, if it is not stretched tightly, that balloon sort of gets absorbed over there. But if it is tight, a lot of momentum can be transferred to. So that's a crude analogy, but I believe yes, the eardrum has to be a bit stretched. It cannot be very loose. You have the bones inside which vibrate. So a tight membrane would definitely help. I think so. Jay, you're on mute. Jay, you're on mute.
Yeah, I can see girls from GNV Uttarakhand, GNV Jharkhand, Kolhapur. Anybody wanted to ask, share, showcase something? Does anybody have brought straws? कोई लेके आया है? Straw लेके आया है कोई? Straw, scissor? Anybody? नहीं. You wanna try later on? हाँ जी, ये जो झारखंड वाले गर्ल्स हैं, आपको पता था, नहीं पता था? लेके आना है कि मिला नहीं? You didn't found that? अच्छा. कोई बात नहीं. What about the other audiences? आप कुछ कहना चाहेंगे? Anybody wanted to know? Speak, share anything from the Uttarakhand girls? No?
अपना एक्सपीरियंस भी शेयर कर सकते हैं. आपको कैसा लग रहा है सेशन? लास्ट सेशन से आपने क्या सीखा? इस सेशन से क्या सीखा? एनीवन?
अगर कोई भी अनम्यूट करना चाहे, let me just. So now you should be able to unmute yourself. किसी को भी अगर बोलना हो ना, but it's better कि if you can raise your hands.
Jay, I just want to request the teachers from next activity onwards, they should make sure that the children will sit with the materials required for the activity. If time permits, we'll be able to ask them to conduct it then and there, or they will be able to do it immediately after the session is over. Without that, the theoretical presentation will not make much sense. So whoever teachers are present here, please help the children to access the materials. They're all low cost or no cost. So absolutely there is not much of cost involved in it. It's only a little bit of planning that is required. If you have any challenges, you can even write to us. We will be able to support you. I want Anurag to post this message in the group also. We will make sure that the children will sit for the session only with the materials required for the activity.
Absolutely. So for an example, let's say in the next session, सब्जियों के साथ कुछ बढ़िया सी गतिविधि करेंगे. And we have intentionally kept this session at 3 o'clock ताकि आप बिल्कुल खाना वाना खा के आए, ताकि वो सब्जियों का इस्तेमाल है वो गतिविधियों में आप करें, ना कि उसका सच सलाद खाने में. So next time we are planning to do some beautiful activity with vegetables. So just make sure that, and we'll let you know what this stuff you'll need it. So just requesting the teachers if you can help by arranging, and this is like that is cost too much. आपको अगर 5-10 पीस खीरा वगैरह लाना है या कटर लाना है, उसमें ज्यादा कुछ नहीं होनी चाहिए. These are very handy stuff you get from the market.
From a teacher side, if you have anything to say, also we are here to listen to you.
Absolutely.
Any teacher,
absolutely.
1 or 2 teachers can please take a call.
GNV NM.
Ranjan Kumar, you wanted to ask something. You can unmute and you can speak. You have raised your hand.
Ranjan, you can unmute yourself and go ahead with whatever you wanted to share, ask.
It's really a great opportunity for students.
Yeah, you're saying something, sir?
It's really a great opportunity for also going to be very much useful for students as well as teachers. So our students motivated a lot. Really it is a good opportunity.
Sure. Great, sir. हाँ जी, रंजन सर.
हेलो.
हाँ जी सर.
हाँ. हेलो.
Yes, Ranjan, please speak.
हाँ, हम सुन पा रहे हैं रंजन सर आपको.
Children, it is your program. You should get the materials that are required for the activity. And we expect that you will come prepared for the activity next time onwards. And you will not disappoint us.
Hello, sir.
हाँ जी,
sir. All of you, sir.
Yes, sir. Sir, we are able to hear you.
Hello.
Sir, we can hear you.
You should get the materials that are required for the activity. I think he is not able to. It's okay. So we can now close Jay because they have another program.
Yes, sir. It's already 10 minutes.
Yes.
Thank
you very much. Thank you so much.
Thank you, sir. Thank you for joining. Thank you, Jay. Thank you, Ashutosh, for this wonderful session. And thank you, teachers and students, for joining.
Thank you very much.
We hope that